So one of the things that we can do with this is we can classify propositions. So one of these classifications is a tautology. It's a proposition that is true in every row of its truth table. So you can see here this formula that we have S and P, or it is not the case that S and P. We filled out a full truth table here with, we have 4 rows. We have S and P, where S is true, true, false, false, and P is true, false, true, false. If we go ahead and fill that out, we fill out all of the operators, we find that the major operator for the statement overall is true in every single row of its truth table. No matter what truth value we have for S or P in any combination, this statement is always going to be true. Now, if you think about what this statement means for a second, SNP or not SNP, well, we talked earlier about how, well, a disjunction between, let's say, P and not P is going to include every possibility. It's either the case that P or not P. There's no other option. So because there's no other option, it seems like it's always going to be true that SNP or not SNP. So if we think about sort of what this is actually saying, it makes sense. But we can also just look at the truth table to see that it is in fact a tautology. It's impossible to make this statement false. So logical truths are propositions that are true on any interpretation. Interpretation here again meaning assigning certain truth values to the atomic parts. So no matter what truth values we assign to the variables in this case, the proposition itself is always going to be true. So tautologies in propositional logic here are logical truths. Now, a different classification is a contingency. A contingency is a proposition that is true in some rows of its truth table and false in others. So it's a little bit difficult to see, but our base column on the left here is just S and P. The statement that we're working with is if S, then not P. So the major operator in this case is going to be the conditional. On the left side, the antecedent here is going to be S, and the consequent is going to be not P. We can see that in the first row, if S, then not P is false, whereas in every other row it's true. We can think about what the meaning of something being contingent is, where it's not necessarily the case. So a contingency is how we would classify a proposition like this that's true sometimes, but not all the time. Now, another type of proposition we have is a contradiction, which is, as you would expect, the opposite of a tautology. Well, let's not think about it that way. But instead of being true in every row of its major operator, a contradiction is going to be false in every row of, or in every column of the major operator of the truth table. So here we only have one variable. We have S, so our base column is just going to be 2 rows deep. S can be true or S can be false. And our statement is S and not S. Now, if you think about it for a second, well, it seems like you can't have S and not S. So if this turns out to be a contradiction, that would make sense. But if we go ahead and fill out the truth table, where in every situation where S is true, then not S is false, and then we look at the conjunction where one side's going to be comparing S and the other side's going to be comparing the value of not S, well, it's going to be impossible for the conjunction of S and not S to ever be true. In every row of the major operator here of the conjunction, S and not S is going to be false. So it's a contradiction. No matter what truth values we assign for S, if we're only assigning these 2 values of true and false, then it's impossible for S and not S to ever be true. It'll be false in every row of its truth table. All right. So next, 2 or more propositions. Now, here we're comparing 2 different propositions. There's this big black bar that's separating them out. And on the left side here, we have our base columns with S and P. We only have 2 variables here, S and P. But our first proposition is going to be, it's not the case that S and P. That's one of our propositions. And the other one is it's not the case that S, or it's not the case that P. Now, two or more propositions are logically equivalent when they have the same truth values in every row of their truth tables. Now, the major operator for this side is going to be the OR, and the major operator for this side is going to be the negation. Now, if we look at the truth values for these column, you'll see that, well, in the first row, the truth value for the major operator for the rightmost proposition is false, and it's also false for the leftmost proposition. In the third row, they're both true. In the fourth row, they're both true. And yeah, in the second, third, and fourth row, they're all true. So they have the exact same truth values in every situation where, or in every row. It's important that the truth values here, sorry, let me rephrase this. So just because there's one false and three trues, that's not important. Well, it's part of what's important, but the important thing is that the rows in which these values occur are the same. If the value here was true, true, false, true, and the value here was the same, false, true, 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 these would not be logically equivalent. But because the values of these propositions are true, or identical within the same row, we can say that these two propositions are logically equivalent. Now, this will become important later on when we're doing proofs, because logical equivalency will allow us to change the proposition that we're using to a different one that is more useful to us in that context, but has the exact same, is logically equivalent to the other one. So we're not losing anything there. We would be able to change the meaning of, well, the meaning is identical, the meaning stays the same, but we can go from it's not the case that S and P to not S or not P if one of those is more convenient for us. Because they're logically equivalent, we could use either one of them, so they're interchangeable in that way. All right. Now, similarly, we can compare two propositions, and if we find that they have the exact opposite truth values instead of the same, they're going to be contradictory. So here we have two propositions, if S then P, and our second proposition is S and not P. So on the left, the major operator of the first proposition is going to be the horseshoe, the conditional, and the major operator on the right is going to be the conjunction, the dot. So we can see that when the horseshoe is true, the dot is false, and when the conditional, the horseshoe is false, the conjunction is true. When the conjunction is true here in the third row, when the conditional is true here in the third row, the conjunction is false, and in the fourth row, when the conditional is true, the conjunction is false. So in every single row, they have completely opposite truth values. So we can say that these two propositions are themselves contradictory. All right. Next, we can have two or more propositions that are true in at least one common row of their truth tables. We can say that these two propositions are consistent. Given at least one set of valuations for our truth values for our variables, it's possible for these propositions to be true at the same time. So we have this if S then P, and over here we have S or not P. We can look at, so the major operator here is going to be the conditional, and the major operator here is going to be the disjunction. We can see that in the first row, both of them are true. In the second row, only the disjunction is true while the conditional is false. In the third row, the conditional is true while the disjunction is false. And in the last row, they're both true. So this means that in every situation where S is true and P is true, and in every situation where S is false and P is false, both if S then P and S or not P are going to be true. It's possible for both of these statements, if S then P and S or not P, to be true at the same time, given certain conditions for the truth values of the variables. All right. So conversely, an inconsistent pair of propositions is going to be one where there is no row of the truth table in which both statements are true. There is no consistent valuation. So this means that it's impossible for both of these propositions to be true at the same time as each other. They don't have to have exactly opposites. So, for example, we could have, if we have a proposition that is itself contradictory, it's going to be false in every single row of its major operator, which makes it inconsistent with every other possible proposition, because it's impossible for it to be true at the same time as another statement to be true, because it's impossible for it to be true in the first place. So if we look at this example, the first proposition we have is S if and only if P. The second proposition we have is S and not P. So the biconditional is the major operator on the left side, and the conjunction is the major operator on the right side. So we can see that in the first row, the biconditional is true and the conjunction is false. In the second row, the biconditional is false and the conjunction is true. In the third row, they're both false. And in the fourth row, the biconditional is true where the conjunction is false. So we have no single row where both of these statements are true at the same time. So therefore, no matter what the values of S and P are, our base values over here, it's impossible for both of these propositions to be true. In some cases, one of them can be true, like when S is true and P is false, then it is the case that S and not P is true, but it is not the case that S if and only if P is true. So it's impossible for these two to be true at the same time. So by using the truth tables, we can determine that they're an inconsistent pair of propositions. So this is also, truth tables are also useful for determining validity. So here, informally, an argument is valid if its conclusion follows from or is a logical consequence of the premises. We've already talked about arguments and conclusions and premises so far and what the relationship is. Or more precisely, an argument is valid if it does not have a counterexample. If there's no situation for the premises to be true and the conclusion to be false. So a counterexample is just a valuation where we have some truth values for the variables that allow the premises to be true and also allow the conclusion to be false. So we can use truth tables to determine if an argument is valid or invalid. Now, an argument's going to be valid if it's impossible for the premises to be true and the conclusion to be false. A truth table is good for that because it shows us all possibilities. And if there's any single instance where the premises are going to be true and the conclusion is false, then we know that it's invalid. So next here, I have an example of a truth table for an entire argument. So this argument, there's going to be, the first premise is if S then P. The second premise is not S. So we have therefore not P. Not P here is our conclusion. And the other two propositions are each premises. Now the major operator for the first premise, if S then P, is going to be the conditional, and the major operator for the second premise, not S, is going to be the negation. So if there's any, and the major operator for the conclusion is the negation. So if there is any row in the truth table where the value for the conditional is true, and the value for the negation of S is true, but the value for the negation of P is false, then it would be an invalid argument, because that would be an example of a situation in which it's possible for the premises to be true and the conclusion to be false, and in order for an argument to be valid, the conclusion must follow from the truth of the premises. So we start in the same way. We have the base column here for S and P. S and P are our only two variables. and go ahead and fill these in. And we can see that, so if we fill in all of the values here, we're going to get 3 situations in which if S then P is true, and 2 situations in which not S is true. So we only need to look at the cases in which both of the premises are true. And that's going to be these latter 2 cases. So if we look at the latter 2 cases here, with the last 2 rows, where if S then P is true and not S is true, we can see that in one of these rows, the third row, the value of not P is false. So this would give us a situation where the truth value of the premises, in the first case, if S then P is true, and the second premise, not S is true, but the value of the conclusion is false, so this is an invalid argument. Okay, how about this? So we flip things around a little bit. We still have if S then P, but now we have not P as a premise, and now we have not S as a conclusion. So if we look at the value of not P, we're going to see that it's true in 2 rows, and in only one of those is it also the case that if S then P is true, where the value of the conditional here is what we're looking at. So in the 4th row, both of the premises are true at the same time. And, well, it turns out the value of not S is also true in that row. So we don't have a row in which the premises are true while the conclusion is false. Now, we do have some rows in which the conclusion is false, but in those rows where the conclusion is false, at least one of the premises is false. So if one of the premises is false, it doesn't, and the conclusion itself is false, it doesn't undermine the validity of the argument, because it's possible that the premise there was a necessary condition for the conclusion. So if it's false, of course, the conclusion is going to be false. So this is a valid argument because in all of the rows where all of the premises are true, the conclusion is also true in those rows. Okay, that's all for this section. See you in the next one.